I'd like to welcome you to today's workshop, Teaching Through Multiphysics Simulation. So on the next slide, we'll just have a quick run through of the agenda. As I've said, I'm hosting today's workshop. My name is Harriet Parnell, but we have quite a few nice sessions, the first of which Janos Blocher is going to be presenting, which is an introduction to ANSYS discovery, which will last about 10 minutes. We'll then hand over to Madhumita Kumar, who's going to be doing some demonstration and presentation on our structural aspects of discovery, before handing over to Nick Stefani, who will then be looking at some of the thermal demonstration. We'll take about a 10-minute break after Nick's presentation, just so you can just grab a breather, have a drink, walk around, whatever you want to do. And then we'll hand over to Chris, who is going to be doing fluids simulation and demonstration within discovery. And then we'll conclude about 20 minutes after that. Actually, he might have about a bit longer than that, 20 to 25 minutes. And we'll have a look at some success stories and the supporting resources, particularly that can help educators with discovery. So you can see we've got some Q&A lined up at the end of today's presentation as well, but please keep on adding your questions as we go. Okay. So on the next slide, before we start, some of these I have just run through, so I will just speed through these just not to repeat myself. Please use the chat and Q&A facility, as I've said. If you haven't already, or if you're new to Discovery, I'd like to point out that the access is already provided if you have a campus and all mechanical or CFD license bundles. But you can also put in a request for a free trial for all students. Software is free to download. I would also like to give a quick heads up for those who don't know haven't used Discovery yet, but maybe some of our other flagship models. What you will need is a discrete NVIDIA GPU for live simulation features. We may see that there's certain features within the software that the speakers will be demonstrating today where this will be required. And finally, if you like what you see today, you want a little bit extra information, we're more than happy to arrange a personalised demonstration if you're interested. So do get in touch with us, education@ansys.com. And with that, I'm now going to hand over to Janos, who's going to lead the start of our presentations.
Yes, hello and welcome. So as part of the introduction to ANSYS Discovery, I would like to first provide you with a brief overview of where ANSYS Discovery sits within the product portfolio before talking about where the software comes from, meaning why it's been developed in the first place, what its capabilities are, and why it's catering well for educational purposes. As you can see on this slide, on this overview slide, ANSYS offers a comprehensive software suite that spans the entire range of physics, providing access to virtually any field of engineering simulation. So we have software on materials, structures, fluids, electronics, optics, and then specific packages like cloud offering, giving you access to public computing resources, or the connection section, which allows you to create digital threads and combine all these various tools. So this is just to name a few. Now, today's focus will lie on the 3D design category, specifically ANSYS Discovery. Now, what is ANSYS Discovery? It is a multiphysics tool that allows you to quickly explore different ideas, iterate and innovate using a range of different physics while focusing on the ease of use, which is why it's specifically interesting for students. So you can not only do fluid flow, thermal or structure analysis, but you can also couple different physics to conduct, for instance, fluid thermal or structural thermal analysis. In addition to that, it allows you to run modal analysis as well as topology optimization. Now, to better understand why we have created this tool and why it's particularly interesting for early year engineering students, I would like to start by the origins. So where does discovery come from? Well, it comes from an industrial need, which is commonly linked to saving time and money. So here we see a typical product life cycle in which you start by defining the concept of the product, which is then taken by the design engineers to create the actual design. This is then passed on to the development stage, in which you have the engineers simulating the design to check whether they meet the requirements, before it's then passed on to testing, production, and various other operations. Now, any change or setback which forces this process to go back will be associated with additional cost and time. And the further you go within this product life cycle, the more costly and timely this change will be. Now, by speaking to customers, ANSYS realized that a lot of this back and forth is actually happening between the design and the development stage. So thus we created a tool that would enable designers to perform preliminary simulation on the design to improve the decision-making process. So basically to reduce the likelihood of any pushback from the simulation engineers. So a tool for an upfront simulation was required. Now, there is some requirements associated with this. While designers, they don't generally have the same engineering background to use multiple different complex simulation software, and they also need to run through a lot of different designs fast in a robust manner. Now, this is the reason why ANSYS created a tool to satisfy exactly these needs without meaning to. They also created a tool that is ideal for students because it's just very easy to use, intuitive, and can be used by non-simulation experts. Includes different functionalities into one single tool. This includes, for instance, geometry modeling, so your CAD environment, structural model analysis, fluid and thermal simulation, but also some optimization such as parameterization, topology optimization, and scripting functionalities, as well as the integration to our material selection software from the Granta family, which gives you access to thousands of material data sheets to conduct realistic product design case studies. It does all of this within a very intuitive user experience, a live physics simulation solver, which provides you almost instantaneous results, and you can still transfer all your results to our flagship software like Mechanical and Fluent to do more in-depth analysis. For you as educator, this allows you to focus really on the teaching message rather than on how to use the software or any technicalities, which is why we think this is really good for teaching early year engineering students. Now, all of these functionalities within Discovery are packaged into three main modalities in the software. So starting off on the left, we have the preparation of the geometry for simulation in the model mode. So this is your typical CAD environment with the same integrated direct modeling technology that you know from SpaceClaim, for instance. You can either prepare this within our tool Discovery, or you can import it from any other different CAD files from third-party suppliers. Now in the center, we have the Explore mode. This is the live physics simulation, which gives you instantaneous results thanks to the integrated proprietary GPU solver. And thus, this lends itself really nicely to do design exploration, design of experiments, run through different iterations. And if you found a viable design, then you can still go into the refine mode, where you can run a high fidelity simulation, which runs on the CPU solvers that you're familiar with from Mechanical and Fluent, for instance. So after this short introduction, I would like now to expand on what I've mentioned previously, namely how and why Discovery is particularly useful in education, because we see that there are two categories of students that can really benefit from using Discovery. So first of all, the non-engineering students. So we're speaking of material scientists, biological scientists, design engineers maybe, which generally benefit from including some simulation aspects in their curriculum. But oftentimes, due to the complexity of simulation software, this is not done. Now, on the other hand, you have your engineering students, so your typical mechanical engineers. They will need to learn simulation eventually, and it's already part of their curriculum in later years. And for them, Discovery can actually help bring simulation earlier in the curriculum. So let's say first and second year, and it provides a stepping stone to learning simulation generally. Now, you might be asking, what are the benefits of introducing simulation earlier? So the first one to mention here is it makes students feel like they're engineers from day one. So it's important to inspire students, convey the passion for the subject, and generally increase the engagement. Secondly, it can help in making them understand the importance of simulation and its role in many different engineering applications. And lastly, introducing such a tool really early is not, or the tool itself is not a substitute for not to substitute, but to complement the analytical teaching of theories with visualization of physical phenomena. And taking the example of an engineering curriculum, in your bachelor, you usually start with classes on fundamental topics, and then you start to consolidate those before those concepts are taken to more applied courses, into a master's, and then even into a research. Now, we have the Granta EduPack, our education-focused software for material selection and source for materials data that can support basically across the different paths to the engineering curriculum. We can see discovery being prevalent at the beginning. And then as the curriculum progresses, discovery can then be paired and integrated with other more advanced software such as mechanical and fluent. And obviously, this is just a glimpse of the ANSYS product portfolio, but generally, this gives you an idea where we see discovery fit. And of course, with all that, we can support education from the first to the last day of the curriculum. So why do we think discovery is useful, particularly at the beginning? For this, we have three main aspects to look at. First one is ease of usage. You'll see in a couple minutes by our live demonstration that it's really easy and intuitive to use. If you've worked with fluid mechanical, these are just a bit more complex to navigate. Second point to mention is visualization. So students find it difficult to understand basic concepts, and visualization is a great aid, and the software can visualize basic concepts really quickly. Quick results, so setting up a model and getting results is very quick, which in turn leads to a faster learning time. And in the following demos, we would like to show you these benefits firsthand. And with this, I'll give over to Madhumita for the first structural demonstration.
Okay, thank you, Janos. Hello, everyone. I am Madhumita Kumar, and I'm part of the ANSYS academic development team. Now, let us move on to the fun part, which is using the software. We will be starting with the structural capabilities of ANSYS Discovery. So, ANSYS Discovery has three main structural capabilities, namely static structural, topology optimization, and modal analysis. It is important to note that Discovery can only simulate linear, elastic, isotropic behavior. The contact types that are available are bonded and sliding, and only a 3D analysis is possible in this software. Now, in today's demonstration, I will be showing you two models, one focusing on the explore mode and the other one showcasing some additional features that is available with our refine mode. So looking at the two models on the slide, first we will start with modeling a beam, applying the boundary conditions. Then we will evaluate the results and evaluate the influence of material and cross-section changes. The second demonstration will be about a simple bracket under loading. Using the refine mode, we will carry out a local fidelity adjustment, and then I will show you how to transfer this to ANSYS Mechanical. So let us now move on to the software. So you should be seeing ANSYS Discovery now. So when you open up Discovery, the first thing that you see is our welcome screen over here. So you get a brief introduction to Discovery itself. Here you will see that it has three modes, which Janos already talked about. And you also have a small introduction to our GUI, how it works. So there are small instructive videos over here. And you also have the shortcuts for navigation, which is exactly the same as our flagship software. Same goes for the selection tools as well. We also have a very interactive help function that is available. So all you have to do is click on the F1 button. And when you point at any button on the screen, at that point, you will get an explanation about it. If you look over here, you press F1 and it immediately tells you what the different components are and how it works. So coming to the last part of this welcome screen, over here we have interactive tours that are already provided and built in Discovery. So as educators, it's easy for you to teach the software to your students. You can just have them go through these different instructions, which takes you step by step and teaches you how to set up the model and run the simulation. And in case you want to learn to do, play around with the model yourself, but you don't want to create the geometry yourself, we also have sample files that are available for different type of load cases, which you can use to learn the software. Okay, so now that we finished with the welcome screen, let us create the beam in bending. So over here, this is how the interface looks like. On the left, let me point you out to three important features or areas over here. The first one is the model tree. So this one will get filled as soon as you build a model in here or you import your CAD models. This tree will keep growing. The next is the physics tree, where you will see the material of the model that you're going to be using, as well as the boundary conditions. Over here, you see structural steel, which is defined as the default, but you can feel free to change that in our settings. And the third important area during modeling is the one over here. It's called the viewing arc. This is used to change the view of the model or how the model looks like. If you want to see it in a wired form, you want to see a shadow model, whatever you like. Now, let us see how easy it is to use Discovery to build our model. Let's create the beam cross-section first. So the dimensions were 100 millimeter times 100 millimeter. So all I have to do over here in our direct modeling software is just type in the value. And it immediately adjusts the model accordingly. Now that we have the cross-section, let's extrude the model. So I use the pull tool over here. I'd like to point out that these options are almost exactly the same as what we have in our flagship software, SpaceLane. So it's nothing new for you to learn if this is something that you've already used to. Now I want a length of 1000 millimeters, so I give in that value. And over here, you see how easily we have created a beam. So for me to escape the tool, all I have to do is press escape twice, and immediately you go out of the tool. As I mentioned earlier, now if you can see, the model tree has now a solid inside it. So if I were to build more components into it, this tree would be also bigger. So the next part of the simulation or creating this model and setting it up is applying the boundary conditions. There are two ways of doing this in Discovery. One is the traditional way, and the next one is the cool new halo that we have available. I will be showing you both methods. So starting with the simulation tab, we go here. We know that we want a structural simulation, so I click the drop down and then I say support. Let me apply the fixed support on this end. So you see different options over here. I know I want fixed, so I click on fixed and I select this face over here and I accept this. As soon as I did that, you can see that now there is a fixed support that has been added to our physics tree. So you know that your boundary condition has been applied. Again, to escape this tool, you click escape twice. Okay, so then the cool new feature that I mentioned, the halo, you can open it by clicking on the black hexagon over here. As soon as it opens up the halo. And over here, you see different options. In this case, I know that I want a structural simulation, so I click on the gear and I decide I want a force acting on the other side. So let me click on this phase. As you can see, this is not acting in the downward direction, but it's perpendicular to the face. Now, how do I change the direction? All you have to do is click on the chevron on the right over here. As soon as you do, you can define the values in terms of the X, Y, and Z axis. In this case, I would like the load to be 20 kilonewtons in the negative Y axis. So all I have to do is give minus 20 kilonewton. And you can see that my load has automatically changed, and now it is in the downward direction. So I click escape twice. Our model is now set up. And the model is now ready to run. How do we know this? Over here, if you look at this black hexagon over here, it turned yellow. This area is called the SID, or the Simulation Information Display. When it turns yellow, it means that the model has been set up and it is ready to solve. So all I have to do right now is click on the solve button on the right. And you can see how quickly the simulation has solved. We've got almost instantaneous results. And over here to the right, you see a legend. In this case, currently we see displacement. But if I wanted to visualize von Mises stress, for example, I could do that as well. Or I wanted to look at strain in only the X direction, or the Y, or the Z, you can do that. So let me go back to displacement for now. Just like the viewing arc on the left over here, this arc on the right is known as the results arc. So if you want to show your students, for example, what a beam in bending looks like, you want an exaggerated displacement so that they're able to visualize in their young years how it works. All they have to do is click on this button over here, which shows the deformation. You can even animate this model to get a feeling of how this deformation is taking place. So I'm going to turn these off. Another cool feature that we have in Discovery is we have monitors that are already built in, but you can also define additional monitors that you like. What do I mean by monitors? Over here, we have predefined charts over here. So in this case, for example, you can see that maximum displacement, von Mises stress, and factor of safety have been defined. So you have the values over here. Let us say now I would also like to know the mass of this beam. All I have to do is click on monitors over here and then define the value that I want, or the variable that I want, in this case mass. And I select my body and we immediately get the value for mass. So the next part, I said we will be seeing the influence of change in material. So let us, for example, change steel to aluminum. All I have to do is double click on this. And then in the dropdown, I select an aluminum alloy. And as soon as I did that, you can see it immediately solved the problem. There was instantaneous feedback, and now we have results. And you can even validate this model this way. For example, you can see the factor of safety has decreased, which is expected when you switch from steel to an aluminum alloy. The stress remains the same. Maximum displacement has increased. And we know that aluminum has a lower density than that of steel, so obviously the mass has decreased. We can now also see the influence of the cross-section, but this time we will be doing it with the help of our parametrize tool, where we can parametrize certain geometries or certain load values or thickness and things like that, so we can study the influence of it on the results. So in this case, let us say that I want to study the influence of thickness. So all I have to do is click on the pull tool over here, and I use the ruler tool to see how much it currently is. And all I have to do is click on this tree button to say, okay, add as parameter. As soon as I did that, you can see that this parameter has appeared at the SID right now. So all I have to do is click in here, and I see that this is 100 millimeters. I can even change the name of this to thickness. And let me say I want to try it out for 80 and 60 millimeters as well. So I add 2 more design points. I say 80, 80 and 60. And I run the simulation. Sorry, sorry, this is Murphy's Law. For some reason, it didn't run. Let me retry that again. Okay. Now the simulation has run now, and what we can do is we can visualize this in the form of a graph over here. We can see that, the model is validated over here. We can see that at 60 millimeters, the factor of safety is below 0.6. And as the thickness increases, the factor of safety also increases, which makes sense. So this parameterized feature that we have, the parametric analysis feature of discovery that we have, can be very useful in teaching students the effect or different variables have on the results or the design of the model. Now, let us move on to the second demonstration, which is that of the bracket. Since I have already shown you how the bracket, how boundary conditions work, I will just be showing you what the boundary conditions that are defined in this bracket. Over here, we have a fixed support on the left end of the bracket, and on the right, we have a 200 Newton load acting in this direction, defined by the blue arrow. So let me first start off with the explore mode. I just click on solve. You can see that the simulation has finished running over here. You see the displacement values. In this case, I'm interested in the stress values of the bracket. And over here, I can look at the values. And I notice a stress concentration zone over here. And I'm curious, what is the problem over here? Does the mesh have an influence? Because with the explore mode, you can't really visualize the mesh. What you can do is preview the size of the average mesh by clicking on this button. And when you hover it over here, you can see, for example, it's using a mesh of 0.85 millimeters. But I would like to see the mesh itself and see how it, how it's divided, how the domain is divided, and if I need a finer mesh in that area. So for doing this, we use our refine mode. So all I did was switch to the right over here, and you can see our refine mode. Now, let us say that in this region over here, I would like a mesh size of 1 millimeter. So I just define this area, and then I say 1 millimeter. Sorry, I select this area, click on local, and then say I want a mesh size of 1 millimeter in this area. And all I have to do now is click solve. So the very first thing that you notice is that the simulation takes a bit longer to run. As Janosch mentioned, the refine mode uses our flagship solver mechanical in the case of structural. So it runs through the model, it creates a mesh, and it uses our under the hood mechanical solver, which is why it's taking a little longer. And you can already visualize the mesh, and you can see the mesh is coarser in the other areas, but I would like it finer in this area, which I have been able to achieve using the local fidelity option. The simulation is still running, and now we can see that it's finished running, and now you can see the results over here. In this case, you can see exactly if the result was if the stress concentration area is caused by having too many too many elements in this area, or is it actually a cause for concern? So another cool feature that we have over here is if you want to define a better mesh, or you want to use the features that is available in mechanical after you've done an initial analysis with discovery, all you have to do is click on this button over here, and you can see that it transfers immediately to Workbench. Okay, now let us move back to our slides. So, coming back to another structural capability, this is topology optimization. Let us look at the bracket on this slide. A fixed support is applied to the holes in the bottom, and a load is applied at the top as shown over here. On the right, you can see a GIF of how fast the optimization simulation runs, and we obtain the optimized geometry as shown in the bottom over here. So you can see that we started off an initial geometry that looks more traditional like this, and now once our topology optimization is run, we've got a more optimized geometry over here. It is important to note that topology optimization only works in the explore mode. Coming to the next structural capability, this is modal analysis. I would like to add that modal analysis works both with our explore and refine mode. Let us look at the model setup. In this figure, we can see a tube assembly. The tube is attached to the plates using two brackets over here, and the plates are then fixed. And a remote mouse is added at the top. We can define the number of modes that we would like to visualize. In this case, it was defined as 6. So you can visualize 6 modes to the right over here. So students can get a feeling of how the vibrations look like and how the model, the modal analysis takes place, and if this is a sensible model or not. Now, let's look at a quick summary of the things that I've presented today. So firstly, we used ANSYS. We know that ANSYS Discovery can solve 3D structural simulations. It has 3 capabilities: static structural, topology optimization, and modal analysis. We saw 2 demonstrations. One was the cantilever beam, and the second was the bracket here on the right. Important features to note are the interactive tours and help. We can quickly modify or parameterize geometry thanks to direct modeling. And using the explore mode gives us results that can be visualized instantaneously. Thank you for listening to me today. Now I'd like to pass on the presentation to my colleague, Nick Stefani.
Hello, everyone. I'm Nick. It's a pleasure to be here and present to you ANSYS Discovery. I'm just gonna share my screen. Before we jump into the software, I'm gonna share a few slides. So in the next 20 minutes or so, I would like to show you a bit of the thermal capabilities that are available in ANSYS Discovery. And when we talk about thermal analysis in Discovery, we actually can talk about different things. We can do solid thermal simulation, and in this case, our aim and what we can get from the simulation is to get as results the temperature and heat transfer in the solid body. But also we can do solid thermal plus structural simulation, in which we can not only get the temperature in the solid, but also check the effect of the temperature on the structural behavior. So Mario was demonstrating structural analysis. You can also add some temperature boundary conditions there and see how temperature affects the mechanical properties, because we support some temperature dependent mechanical properties as well. We can do fluid thermal simulation, so in which we can look at the temperature and heat transfer in the fluid, and we can investigate things such as boundary layer. But also we can do the more complex of all of them. We can do solid fluid thermal simulation, otherwise known as well as conjugate heat transfer, in which we can check the temperature both in the solid and the fluid, investigate boundary layer, and also investigate the heat flux on the fluid-solid interface. Now, as part of my demonstration, I'm going to focus on the solid thermal capabilities, but later on, Christopher, in his fluid demonstration, is going to touch as well on fluid thermal and conjugate heat transfer. Now, when we speak of solid thermal, we have at our disposal different boundary conditions in ANSYS Discovery. First of all, they can be accessed through the simulation tab. in the same way in which you have seen structural boundary condition, we have solid thermal panel. And these are 4 of them. You can set up a fixed temperature on a face or a body. You can set up a convective heat transfer on one or more faces. You can set up a heat generation rate on one or more faces to simulate a heat source or a heat sink, or you can set up some level of insulation as well, in which no heat will be gained or lost through a selected phase. Now, by combining one or more of these, we can set up our thermal simulations. What I would like to show you today is really along the same lines of what Maru has done, and as a common thread from this workshop, is to show 2 different examples. One, how to set up a very fundamental problem, a heat transfer in a film, which is a classic problem which is done in any very introductory class in which students have to start to deal in heat transfer, usually a first-year engineering course. And the idea is that we have this fin of a radius of 50 millimeters and a length of 40 millimeters. We have 2 fixed temperatures, on the one of 20 degrees and one of 100 on the 2 surfaces, and we have an insulated surface in the middle, and we have a thermal conductivity of steel. So what we'd like to show you is how we could use this kind of problem for your teaching. And the idea is that you could ask the students to solve the problem analytically and numerically to find the value of heat flow and compare the solution. And this, we think, it could be a very good fit for discovery, because it's very easy and quick to do this simulation. But there's a lot of potential in students learning that it's very important to validate both their analytical and numerical solution. And the best validation is that you do 2 separate analyses and the result match. But also we can use simulation to visualize the temperature field, and that's another benefit of a simulation, and in this case introducing discovery, visualization of the state variables. But we can also do 2 other interesting things. One is verify that the directionality of the heat flow is in line with the sign convection, so from hot to cold temperature. And also we can verify energy balance in our geometry. So this is a very simple example, but hopefully can give you an idea of how we can use discovery to introduce students to this concept. And then we're going to move to a more applied problem, a bit more interesting, of how to design a heat sink to be placed above CPUs, but we'll look in more details on this example later. Let's start with the first one. I'm just going to switch to discovery. Hopefully you'll be able to see the software. So the first thing I want you to do, like Manu, is draw the geometry. The great thing about discovery is that we can do both geometry editing and simulation in the same software. We want to draw a simple film. Before we had rectangular cross-section, now we're just going to have a simple circular cross-section of 30 millimeters diameter. So we have our cross-section. Next step, we're going to extrude it by 40 millimeters. And once we have our geometry, all we need to do is to set up the boundary conditions. So for this, we go to the simulation tab. We have structural, fluid, and thermal. In this case, we're going to use thermal boundary conditions. We want to have a fixed temperatures on each of the faces. One of 20 degrees Celsius, and another one of 100 degrees Celsius. Plus, we want the middle part of our billet to be, of our fin to be insulated, so we can insulate the surface. Now, if we review our boundary condition on the left side, in the physics tree, we have structural steel as a material, which has thermal conductivity that we're looking for, but also this can be changed. We have insulation on this middle surface, then we have temperature on one side and a temperature on the other side. So all we need to do really is run the simulation now. Thanks to the GPU solver, we can see it takes like very few seconds. Solid thermal simulation are very, very fast in discovery, and we can see straight away the temperature distribution. Another thing that we wanted to check the directionality of the heat flow. And for this, we can actually plot the heat flux vectors. And we can actually maybe make them a bit bigger to see what we're looking at. And we can see that the directionality is maintained. Again, this can be pretty obvious if you have this kind of geometry, but if you have a complex geometry with different heat sources, even verifying which direction heat is flowing, it might be actually not trivial. But another thing that we wanted to do, we wanted to check what was the heat flow on the faces and compare it to an analytical solution. Now, to do this, we can use the monitor feature that Madhu was showing, and we can create a custom monitor. So we're going to click on monitors, custom, and then select the variables that we want to look at, in this case, heat flow, and the surface from which we want to get heat flow. In this case, from one of the faces, and we can see that we get a value of minus 71.4. But an interesting thing to see is to see, okay, what is the heat flow on the opposite face? And if we click, we can plot it there as well. And we can see that on the two faces, on one we have minus 71.4 and the other one 71.4, showing that there's energy balance and any heat coming in the geometry equals to the amount of heat coming out. Now, this is a very simple examples, but hopefully what I would like to convey is how easy and quick it is to do it. And so how easy and quick you should be able to implement it into a lab supporting more fundamental teaching and complementing the teaching of analytical theories, which are important and we don't want by any way move away from. And if I'm just going to go back very quickly to the slides, we achieve everything we wanted to do. Here we have the analytical solution, and we can see that we have a delta between the two solutions of less than 1%. And again, this is a very simple exercise, but hopefully can give you some ideas of how the software can be used for fundamental teaching. A bit more interesting or fun, at least for me, is a bit more of applied problems. So we have the heat sink, and why do we need that sink at all? So electronics components such as central processing units or CPUs can actually generate from a few watts when they're idle and your computer is not doing almost anything to nearly 100 watts of heat during high computation. For example, when you're running simulation software, really to high temperatures. However, these CPUs, they must run under 70, 80 degrees to be fully functional and efficient. And heat sinks are components that sit on top of the CPU that should draw away heat from the CPU through conduction and dissipate it through the surrounding air by convection. So in this problem in Discovery, I would like to show you how we can tell a story regarding the heatsink and perform almost a design analysis in which for the given heatsink assembly, we want to keep this CPU temperature below 70 degrees. Now, one great thing that we have in Discovery is that we already have some pre-made example. As Madhu was showing, we have the bracket, but we have also for different physics, where we have the bracket for static stress, one for topology optimization, some fluids ones, but also we have this great heatsink thermal geometry already present, and it's plug and play, so you'll be able to play with it straight away. So I'm just going to open it up, and we're going to look at what's included. I'm just not going to save the previous simulation. So we have open the file, which is available to everyone. Let's see what we have. If we start from the bounded contacts at the bottom of the in the CPU geometry, because that's where heat is generated. We also can make use of monitors. And if we plot the monitors, we can see the monitor of the maximum temperature, which we can assume it's always found in the CPU because that's where heat is generated. And so we can use it as a proxy for measuring our temperature. And we want this to be below 70 degrees. And now everything is fine because it's 45 degrees. So everything is working well. Our CPU is within the acceptable range. However, what's going to happen when we're going to start using our computer and do computing intensive things, more heat is going to be generated. As I mentioned before, we can go from a few watts to almost 100. So let's see what happens when I change this boundary condition from 10 watts on heat generated to 100. Just going to change the number. Simulation is updated live, and we can see we go from 45 degrees to 256. And this is too much, and it's not acceptable because probably our components will start melting and not functioning properly anymore. We need to solve this problem. So how can we solve this problem? Well, we have different tools in our arsenal with Discovery, and these are really represented into the physics tree. First of all, we have the material. So we are using aluminum as the material for the heatsink, and aluminum is a good conductor. That's why it is used, because it's able to radiate through itself heat pretty well, to conduct heat pretty well. So, but are there any better conductors? Well, copper is usually a better conductor than aluminum. So what we can do, we can maybe try to change the material, the heatsink material from aluminum to copper, and see if we can get some improvements. Which means, let's see if we can bring the CPU temperature down. So we have a vast material library here in Discovery, and we can look for the material. In this case, we want to look at copper. We have a record for high conductivity cast copper. We can select the material, and we can see what happens. So we can see that from 256, we go down to 234. So we went into the right direction. We were able to bring temperature down, but this is not nearly enough. We need more. We need to go below 80 or 70 degrees. So what we can do, let's go another step. We change the material. Another great feature that we have in Discovery is integrated geometry modeling. So as Madhu was showing, we can make changes to the geometry live and see how this affects the simulation. Now, since the heat sink dissipates heat through convection, the bigger the convective surface, the bigger its ability to draw away heat. So what we can do, we can modify the design, and we can make all of these fins a bit longer, a bit larger to increase the convective surface. All we have to do, we have to select the pull tool, select one of the top of the surfaces, and then we could select one by one holding control, but that's not a very nice things to do, and it can be quite tedious. So luckily in Discovery, we have a power select tool that allows you to make smart selection. For example, we can select all coincident faces and automatically select all of these ones for us, which is very convenient. And then we can select by how much do we want to extrude them forward, for example, 5 millimeters. We can see a new geometry. The geometry is updated. The simulation as well is updated live. And we can see that we were able to bring down the temperature. So from 234 to 200. And at this point, we might see, well, all we have to do is keep increasing the size of the heatsink, which in theory could work. However, there's always a space problem when we talk about electronics. We want our computers to be as thin as possible, our phones to be as thin as possible. So it's not that we can make a heat sink which is 20 centimeters long, because it wouldn't fit in our phone or in our computers. So we're quite limited to how much bigger we can make it. So we are back to the drawing board. And as for inspiration, again, we need to go back to the physics tree and see what else can we change. And we change the material, and we cannot really change the heat generation because that's a given by the things that we're doing. But what we can play with is the convection coefficient. Well, one theory, we have the heat transfer coefficient and the outside temperature. Well, one thing it could be that we could put our computer in the fridge or in the freezer, but that might not be the best solution and very much practical. But we can maybe affect the heat transfer coefficient. And as I mentioned before, this value of 10 represents natural convection, but we know that actually what we could do, we could move this to a forced convection, which means just air which is pushed through the heatsink. And this is more representative. This can be represented with a heat transfer coefficient of a value of 100 compared to 10. So if we do this, we change this value to 100 by representing forced convection, and we can see how temperature goes down from 200 back to 57, which is more than acceptable range. And the reason why, and this shows, and this is actually a little story that shows why computers have fans. And in computer, and if you could hear my laptop, you could hear the fan going while I'm doing simulation. The only way that computers can actually deal with the heat generated by CPU is by using fans leading to forced convection and a high heat transfer coefficients. So that's it for my demonstration. Hopefully this can give you an idea of the type of stories that you can build with Discovery. And thanks to these really fast simulation results, it's really easy to go through them with students and link them to fundamental concepts and try to, as you've seen today, look at things like thermal conductivity, convection, generation of heat, and many other important concepts. Going back to the slides, just as a summary, in Discovery, you can do numerous thermal simulations, such as solid thermal, but also structural thermal, fluid thermal, and conjugated transfer problem. And one example of a conjugated transfer problem that we could do, we could actually simulate in Discovery even the fluid flow of air traveling through the heatsink. And you could even expand this further by doing parametric analysis and check at what airspeed is required to bring the CPU below 17 degrees. And then maybe ask the students, okay, we need a particular velocity of air, for example, in this case, at least 9 meters per second. What kind of fan would we need to buy to achieve that speed and in that basically maybe limited space? And the last thing that I want to leave you with is something that unfortunately I didn't have time today to show, but and we only look at steady state analysis in Discovery, but actually we also have the possibility to do transient analysis in Explore, which is something that can be useful to see how the temperature distribution and the state variables change over time. If you're interested in any of the things that we couldn't cover today, or in general, if you're interested in Discovery, please feel free to get in touch with us. We're always happy to do tailored demonstration based on your teaching.
Hello, everybody, and welcome back after that 10-minute break. Hopefully you have all rejoined us again. I am now going to hand over to Christopher Blomberg, who's going to be presenting the next part of our workshop.
Thanks a lot, Harriet. Perfect. So, yeah, also from my side, everyone, thanks a lot for joining the call today. My name is Christopher Blomberg. I'm an application engineer in the Discovery team based in Zurich, Switzerland. And today, I'm going to be going over some of the fluid simulation capabilities that we have inside of ANSYS Discovery. The outline of this brief demonstration, we're going to start off with basically a summary slide on the fluid capabilities, the current status today. Of course, we have a pretty dense roadmap, so new things will come out in the future, but I'll show you what we have today. And then please reach out to us if you have any questions about other features that you're interested in using. Then we're going to jump straight into two demos. The first one's the simple mixer T demo. I'm going to show you some basic steps, for geometry prep for fluid flow. So, extracting a fluid volume, for example, from solids, setting up your boundary conditions and running the calculation. Then we're going to have a look at some monitors, do, a quick analytical check that everything is indeed okay. And then I'll show you how to parameterize some boundary conditions. I think my colleague Madhu before was showing how to parameterize geometries. Here you can also parameterize boundary conditions. Then the second demo is going to be a little bit more complex in the sense that we're going to simulate a traction inverter and do a heat transfer calculation there too between fluid and solid, so conjugate heat transfer simulation. Again, we'll go through the problem definition, understand why some kind of forced convection is necessary, and then investigate at the end some different cooling channels. Steady state flow solver. We can also do transient flow, but that's limited only to Explorer mode, so the live GPU solver mode. We can calculate both incompressible flow and compressible flow. However, for compressible flow, since it's a pressure-based solver, we recommend to stay below Mach numbers equal to 1. If you want to go above that, probably density-based is better. So your best solution in that case is to jump to a flagship tool such as Fluent. Then we can also solve porous media in both modes, so Explore mode and Refine mode. And we can also do conjugate heat transfer calculations in both modes, so Explore and Refine modes. Great. So let's jump into a short demo. The first one is a mixer T, where we're going to set up our boundary conditions, where we're going to have one inlet on the left-hand side here, another inlet on the top, and an outlet on the right-hand side. Our materials are going to be, for the fluid flow water, the casing around it, so basically the pipes and everything. Those will be structural steel. But to start off with, we can just we can do some geometry prep operations to extract the fluid volume. So let me exit the presentation. Great. So here you can see the solid geometry, and as a first step for fluid flow, if I can close this. Okay, good. Sorry, there was something from WebEx that was blocking me from selecting this tab. So we can go to the Prepare tab and select Volume Extract. So this is a typical, geometry prep step that you typically have to do when you are simulating fluid flow, because you get a solid volume, you want it to be watertight. So you select the capping faces, you select the seating face, which is basically a wetted face in contact with water. And then I like to use this preview inside faces feature just to check if all the red faces are indeed contained in the geometry, meaning that it is watertight. If it, for any reason, is not watertight and you see these red faces, everywhere, basically, you can go and use this animation slider bar here to understand where it's flowing out and, quickly go back and fix your geometry accordingly to make it watertight. In this case, everything's okay. So I'm going to just confirm the volume creation, fluid volume creation. You can see that here afterwards in the geometry tree. And then we're going to set up our boundary conditions. So again, I'm going to go to our halo, brings up our head-up display, set up our fluid flow boundary condition. I think on one side it was 0.1 meter per second, on the top 2, and then on the right-hand side, we have an outlet with 0 Pascal relative pressure. As a material, as a default for fluid flow, it's water. Of course, you can change this if you want to. We have a big database of materials. You can also change the material properties yourself. Save that in your local database to use afterwards if you want to. In this case, I'm just going to use water. And we can start our simulation. Now, we're in Explore mode, so that's a live GPU solver. We're going to get our almost instantaneous results. So what we're seeing here are kind of curved vectors, but, you can also do, sometimes this one is nice to see the direction field, for example. If I put it this way, yeah. So you can get a little bit more information. You can see first of all, your velocity magnitudes, and then overlaid on that kind of the streamlines. See where you have the recirculation zones and whatnot. Good. So one thing that I want to do, a check that I want to do, is to see if mass conservation is indeed is basically how do you say, respected in that sense, that this calculation is conserving mass. What's coming in is what's going out, nothing more, nothing less. So what I'm going to do is set up a monitor on this outlet, and we can set up velocity, for example. Then we can rename this to outlet or average velocity outlet. And you can see that the value here pops up on your screen. And if we go back to the slides now, we can bring up some equations. And, basically conservation of mass says, mass flows that's coming in is equal to mass flow that's going out. And for incompressible flows, we have basically the mass flow that's equal to density times velocity times surface area. So if you plug everything in and solve for the velocity on the outlet, you basically get this result. And if I bring up the screenshot again from ANSYS Discovery, you can see that the value is basically identical. So we do have mass conservation in that sense. So that was just a quick check there. Good. So now the next thing that we're going to do with this calculation is add a little bit of complexity. We're going to actually include the solids and do our first so-called conjugate heat transfer calculation, where we include the heat transfer, the heat exchange between the two. So first off, I'm going to set up a thermal boundary condition on the inlet down here. Let's set that to 25 degrees Celsius. On the top one, we can set that to 50 degrees Celsius. And then what I'm going to do is include the solid in the calculation. And you can see here that my physics tree just got a little bit more complex. I have more things in it. First off, we have convection that has been automatically defined on all outer surfaces on our solids. Then we have bonded contacts also between our solids, since it is indeed a multiple component part, as you can see here in the geometry tree. And then we also have our conducting non-slip wall, which is basically the fluid-solid interfaces. Those have also been automatically defined in ANSYS Discovery. So one last thing that I actually want to do is set up some insulated faces. So here, set up one insulated face on this side, one over here, and then as the last one, let's set up this one here. You can see here, let me just start to solve. You can see in the middle of your screen on the bottom here, this is called the SID, Simulation Information Display. And if you hover over it, you get information about what you're simulating. So this is a steady state fluid, thermal fluid solid calculation, and it's solving. Basically, you can see that it's solving, it's iterating to converge with this white little line going around the SID. You can also see these two icons. This also indicates kind of what you're simulating. Basically, so this is a 3D rendering of temperatures. We can also just set outer temperatures to see a little bit, how the warmer flow coming in from the top is kind of contained to this upper region of the pipe on the outlet, meaning that, this piping is probably getting warmer on the top compared to the bottom. So you're going to have a temperature gradient, maybe something that you want to take into consideration. Another thing that we can do is, for example, for inlet flow 1, we can add that as a parameter. So we can add the boundary condition as a parameter to set up different design variations. So I can set up a second one where I add a variation, dV2, to 0.2 meters per second. And, then we can update basically all of them. And we're going to get pretty much, for these two design variations, this demo, it's quite simple, only two, but you can imagine you can do a bunch of them. And then, you'll get your design variation table. You can see the relationship between, your parameter and basically anything that you have in your monitors. So here you can see, increasing, of course, the flow on inlet 1. What is it going to do? It's going to push up this hot flow a little bit higher, contain it to a little bit, a higher region on this outlet section of the piping. Good. So we can go back to the slides. That was the first demo. So the second demo is about a traction inverter. Traction inverter is a device used often in the automotive industry. It's a power electronic device where you basically convert direct current to alternating current and vice versa. And, you typically have IGBTs that get pretty warm, and you need some kind of forced cooling to bring, the temperatures down to reasonable values so the whole thing doesn't melt. In this demo, we're going to use the following materials. So fluid. The fluid's going to be water. The housing is going to be structural steel. IGBTs are going to be silicon. We have our boundary conditions here. So the external convection is going to be, with a convection coefficient close to what we would expect from natural convection. So this value here, 3 watt over square meter Celsius, and an ambient temperature of 22 degrees Celsius. Then we're going to set heat sources on all 4 of the IGBTs, equal to 400 watts, so 1,600 in total. And we're going to have an inlet flow at 2 meters per second and 25 degrees Celsius to cool the whole thing down. So that's our forced convection. And then we're going to have an outlet at 0 Pascal relative pressure. Good. So let me jump to that second demo. Here we can see the traction inverter. You can see the complexity of the IGBTs here. Let me just select them from the geometry. You know, in reality, they'd be a lot more complex than this. You probably have, you know, PCB on it and a bunch of different chips and whatnot, cabling and everything. But here we just blocked them all together because this is really a conceptual tool meant for, you know, early phase, meant for the early phases of product development. So, you know, the amount of complexity and the type of questions that you can ask and answer with ANSYS Discovery are indeed not too advanced in that sense. I mean, here you can just understand pretty much the cooling power that you need, and you can modify a bit the cooling channels to understand, you know, which concept looks the best. So here I'm going to set up a heat source. We can put that at 1,600 watt. And then I'm going to also change the materials here. Just a sec. Set this to silicone. And the rest of the housing, we'll just leave it as structural steel. We can start up our simulation just to see how hot everything gets without any type of, you know, forced intercooling. And actually here, the convection coefficient, I left at 10, which is the default. If I change this to 3, you'll see, as before, you know, simulation starts up again, updates immediately. We're at maximum temperatures of around 1,136 degrees Celsius, so way too hot. We need to cool this thing down. So what we're going to do is, if I hide these two components, you can see we have some cooling channels here. So basically what we're going to do is first extract the fluid volume, because we're going to simulate the fluid flow together with the heat in the solids and the heat exchange between the two, so a CHT calculation. So let's go ahead and extract the fluid volume. Volume extract, we can preview the inside faces. Oh yeah, here I made a mistake. Let me show all again and do the exact same thing, because there it wasn't closed off on the top. There we go. So now it's contained in there. Preview looks pretty good. I can confirm by clicking on the green check mark, and then I can start setting up the boundary conditions on the fluid part. So here we said it was 2 meters per second. Then we wanted 25 degrees Celsius. On the outlet, we wanted 0 Pascal, and a recirculation, we just leave it at 22 degrees Celsius. And that is pretty much our calculation set up. You can see here in the physics tree, we got our solid thermal boundary conditions, we have our fluid flow boundary conditions, we have our connections, so bonded contacts between the solids, and then our fluid-solid interfaces. So let's start the calculation and see if the maximum temperatures are lower now, and hopefully around a more reasonable value that won't melt everything. So here we have, as you can see, we're around 75 degrees Celsius. We can look at the outer temperatures. If you hover over a certain location with your mouse, you get the exact value on the color scale. So here you can see the top IGBT is indeed the hottest component. It's around 75 degrees Celsius. You can actually also show maximum and minimum locations. So maximum's up here on the IGBT, minimum is somewhere down here, or in the fluid flow itself, probably close to the inlet. And then on the bottom here, you can see we have, you know, much cooler IGBTs. So, you know, the efficiency of this cooling channel is probably not as uniform as it should be. You know, you could probably consider redesigning it so that you have maybe a couple more zigzag channels passing underneath this upper IGBT to cool it down a bit more and get it a little bit closer to the temperatures on the bottom. So that's some kind of design variation that you might want to consider. In any case, you can see, you know, these maximum temperatures now are at much more reasonable values. So here we can see, you know, why we need some kind of internal forced convection. In this case, liquid cooled, and you know, that's basically what's being used in industry today. A lot of your automobiles probably have this device in it too. Good. So the last demo I want to show you today is, again, this IGBT, and we're going to be looking at pure isothermal fluid flow calculations, horizontal cooling channels, ribs. Then we have vertical ones. Then we have some pins, and as the last one, there's these super thin channels that are basically guiding the flow all the way from inlet to outlet. And so we just want to see which one behaves the best in terms of, recirculation zones, pressure drop. If you have too many recirculation zones, those are kind of areas where you're losing potential energy from the flow to extract heat from your system. So you want to kind of avoid those if possible. Just visually, we're going to look at where those are and how we can, and which design variation looks the best. So let me set up the fluid flow, then we can look at it from the top. Start up our calculation. Let me do these little kind of weightless particles that are showing kind of the fluid flow. Here you can see the first design, of course, no real obstacles between inlet and outlet. It's letting the flow pretty much do what it wants to do. And, we have a big recirculation zone here, so that's probably not the best design. I'm going to activate now the first rib design. This is actually the one that we had in the previous CHT calculation. I'm going to update the volume in context, so we get an immediate fluid volume update based on the geometrical change of the solid. And here we can see how that impacts our fluid flow. Looks a bit better. Of course, this big recirculation zone here that we had before is not there anymore. We can look in terms of pressure drop. Yep, it went up. Since we're adding more obstacles between inlet and outlet, you need a little bit more power to pump water through this system. Then we have the vertical ribs. So let me update the fluid volume in context again.